Welcome to the Data Science Seminar. It's my great pleasure to welcome our speaker today, Piotr Antonik from Central Supélec Metz campus. Piotr did his PhD in Brussels, where he studied implementations of machine learning methods in photonic systems. His PhD thesis won the Springer Thesis Award and was published in the Springer Thesis Collection. Since October 18, he is Associate Professor at Central Supélec Metz campus. His research activities combine machine learning, photonics, and FPGA programming, with applications in telecommunications, computer vision, and biomedical imaging. Today, Piotr will talk about machine learning at the speed of light. The stage is yours.
Okay, thank you very much, Doreen. Hello, everyone. Good morning. Thank you all for coming. It's my great pleasure to talk to you about a subject that I'm actually very passionate about, the use of optics to do computation and to do machine learning. So a simple example, let's start with that. A simple optical lens, so a simple piece of glass in a particular shape, can be used to do the 2D Fourier transform of an image, which is a rather complex mathematical operation. So here is an example. We have the image on the left. Can you actually see my cursor when I point it around? Okay, good. So we have the input image here on the left. We have the computed Fourier transform on the right, down on the computer, and the optical result here in the middle. So consider, let's say we have an image of 3000 pixels by 1300 pixels. It's a medium-sized image. Taking its 2D transform on a computer would take approximately 30 seconds. And with optics, with our simple piece of glass, it would be done instantaneously because it's just the time the light propagates from one side of the lens to another. Now let's increase the complexity of the task. Let's increase the size of the image from 9000 by 4000 pixels. On a computer, it would take around 10 minutes to compute the 2D Fourier transform. And with a lens, it's still instantaneous. This is quite fascinating, isn't it? Well, the idea of using optics to do such computations has actually been investigated for decades now, but so far the Boolean digital computing is the big winner. Well, now may be the time to reconsider this idea, and for several reasons. First, the optics are becoming better and better. The electronics, on the other hand, are approaching the physical limitations of what can be done in terms of miniaturization. And the Boolean logic, our standard way of doing computations today, might no longer be the smartest one to do. In this talk, I will show you some of the recent advances to the optical computing with recurrent neural networks. And I'll try to convince you that investing into optical computing in the future is not such a bad idea after all. Okay. So the idea of computing has actually always captivated the interest of humans. One of the earliest computing mechanisms is this Antikythera mechanism that is dated back to 200 years before Christ, that calculates the moon phases in the lunar calendar from a simple input, a date that you set turning a handle. Sometime later, in 1941, Konrad Zuse realized his digital electronic computer, the Zuse 3, applied to the calculation of mechanical properties of airplane wings, and he introduced a very important property in computing, which is their reprogrammability. We don't want to go much deep into detail in the history of the computing, but what I want to do is to highlight this transition from the mechanical substrate to the electronics, which greatly benefited the computational power of the device. And today we will discuss the possibility of another shift, now from the electronics to the optical substrate. Let's consider the electronics and the photonics from the point of view of their elementary particles. Represented here in this table, we have the electrons and the photons, which became fermions. Sorry, it's a mistake on my side. Here we may notice some fundamental differences. So the electrons, as I said, are fermions. They have a charge, and therefore they strongly interact. The photons, on the other hand, they are bosons, they don't have a charge, and they do not interact. So which substrate, photonics or electronics, is best for computing? In 1990, Lohmann tackled this question of what exactly is required to do computations and identified two key ingredients. First is logic or interactions, which is here, and the second is transportation or communication. This view is strongly biased to the binary logic, so we will replace the first ingredient, which is logic and interactions, by a more general term, the nonlinear transformations, which also include logical operations. So let's get back to our particles. Because of their fermionic nature, the electrons strongly interact and they are well suited for nonlinear transformations. On the other hand, these very interactions are a problem in the transportation capacity, making them quite mediocre for information transportation. The photons, on the other hand, do not interact directly. Therefore, they are perfect for the communication, and this is something that we experience in everyday life with the fiber optics communication. But it's also a problem when we want them to interact, because actually they don't interact at all. And to induce any interaction, we need actually a physical medium as a mediator to introduce interactions between photons. So from this table, we may conclude that neither electronics nor photonics are actually perfect for computing. Judging from the past, the electronics and photonics remain locked somewhere between synergy and competition. Actually, the first books on optical computing were published in early 1970s, and we all know that now electronics is the big winner. However, this decision is strongly biased towards the Boolean logic and the serial architecture used commonly for computing. Already today, the performance of standard CPUs is limited not by the size or the performance of the individual transistors, but rather by the energy it consumes inside very small volumes of the substrate. A significant fraction of energy is actually dissipated through interconnections. Let me give you some figures to illustrate that. The energy just to switch a transistor or to switch a flip-flop in a standard CMOS gate ranges between 40 attejoules to 3 femtojoules. It's a very small quantity of energy. On the other hand, switching an interconnect of 10 millimeters of line consumes 100 times more, 600 femtojoules. This high energy consumption becomes even more crucial in neural networks, whose fundamental feature is the large-scale connectivity. So based on their physical properties, it makes more sense to use integrated photonics for signal transmission in the next generation of neural network hardware. And the industry is actually shifting focus to this idea. Now, let's remember that Boolean logic is not the only way to do computation. A different approach to computing is based on the spatial properties, spatial nature of optical imaging. As I told you, a single optical lens transforms an arbitrarily complex image input or a waveform simultaneously in parallel. So let's consider again its capacity to do the Fourier transformation. If we have a simple lens here, an image in the focal plane, then we get the 2D transformation on the other side on the focal plane. A popular application of this optical transformation is the realization of the convolution operation, which also is a complex operation. It's very needed in the domain of modern convolutional neural networks. Another example of more fundamental mathematical operations have been demonstrated also in optics. A good example is the optical perceptron. The research into optical perceptrons was highly active in the late 1980s. Among others, the holographic realizations appeared particularly interesting, as illustrated in this simple example. We have here a simple hologram, which is created by the interference of the weights of the neuron, the W, loaded here in a spatially extended beam. And on the other side, we have just a reference beam that interferes with the weights and creates the hologram to record the information of the W's in the hologram. If then we illuminate this hologram with the state X of the network, Well, the hologram will produce the output, which will contain the information of W multiplied by X. So basically, this hologram implements the matrix multiplication. And what is very fascinating is that under certain conditions, 1 cubic centimeter of the holographic medium can store up to 10 to the power of 10 interconnections, which is a huge amount of information. Unfortunately, despite the elegance of the first implementations of optical perceptrons, they still have some drawbacks, namely their inefficiency. And this is again the inefficiency of interactions in photonics. Holographic coupling is fundamentally limited to the diffraction efficiency, which often lies below 10%. And furthermore, our experiments are based on free space optics, which are bulky experiments, and it's not apparent how this holographic concept can be translated or integrated in photonics on chip. Another argument against digital computing is that our modern digital computers are strictly accurate devices. Already in 1965, von Neumann discussed how to approximate high-precision digital computing with unreliable components, introducing redundancy and majority voting. So basically, he derived bounds to prove that with enough redundancy, error probabilities can be pushed below any desired threshold. However, these bounds are based on assumption that all the errors are independent. When the errors are correlated, which happens in most physical systems, an ensemble system still works, but we don't have the proof of the convergence of the accuracy anymore. On the other hand, we might ask a simple question: do we need the precise computation in our applications? This is especially relevant for tasks such as image or sensor processing, where small errors are usually acceptable. Consider this image. If the colors of the people of their clothes change slightly, or if the shapes of the car of the people change slightly, we'll still be able to recognize them, right? From the energy perspective, it's no longer the most efficient way to record the data as numbers or as sequences of bits in a precise way, and to apply the precise mathematical models on them. Neural networks, on the other hand, handle such inaccuracies without much problems. So, in conclusion, we have seen that optics still struggles to beat the electronics in the game of Boolean logic, but has all the potential to shine with the neural networks, whose architecture require interconnectivity and massive parallelism. The recent surge in the activity of neural networks awakens again this interest to photonic computing, but still there is this problem that controlled connectivity between the nodes is difficult because of the low interconnectivity of photonics or of photons, even with the new media that we have right now. So the question arises: can we still do neural networks with limited connectivity? So not really the fully connected neural networks. Can we sacrifice this connectivity? And the answer is yes, we can do that. This principle is called reservoir computing, and that is actually what we're going to talk about in the next section. So, reservoir computing itself is rather an abstract computational model. It consists of two parts: a reservoir here and a readout layer. The reservoir is a dynamical system that is perturbed or driven by a temporal signal u of t, which affects its current state, that we will denote x of t, and the future evolution of the state. In the readout layer, we observe the reservoir's internal state, x of t, and we build an output signal y of t using a linear model. In contrast, so when we train the system, we only train the readout. We leave the reservoir untouched, which is a dynamical system that we don't train. We only train the linear model that is built on top of the reservoir so that it can solve the task that we want to solve. A very neat application of reservoir computing is literally in a bucket of water. The reservoir state is, in this example, is the surface of the water in the tank. It can be perturbed by applying a temporal signal that we can transfer to the surface through these rods that are actuated by electrical motors. And we also have a camera here on the top that takes a picture of the surface, which observes the reservoir and takes a picture of the surface of the water. The reservoir computing approach emerged almost simultaneously from two fields, neuroscience and artificial neural networks. The two most frequently cited papers are those by Herbert Jaeger and Wolfgang Mass. They used echo-state networks and liquid-state machines, LSMs, respectively, as their reservoirs. The two are models of simulated recurrent neural networks that operate in discrete or discretized times. The liquid-state machines are a model of simple biological spiking neurons, and they were not deeply studied in optical community. So we will leave the liquid-state machines aside for the rest of the talk and focus primarily on the echo-state networks as our model for reservoir computing. Echo-state networks consist of discrete time analog neurons, so it's a recurrent neural network, often with a sigmoidal or a hyperbolic tangent activation function. The network can be fully connected or sparsely connected, and the input signal is distributed equally to the full network. The network's internal space is finite, and it consists of all the states of all the neurons. Mathematically, if we use bold small letters for the vectors and capital letters for the matrices, the evolution of the system obeys these two simple equations. Here we have the U of n, which is the input signal in the input time series, which can be one-dimensional or multi-dimensional. We have x, which is the internal state of the system. And we have the hyperbolic tangent here, which is the activation function. We have also the input weights, which distribute the input signal to the nodes. And we have the W matrix, which contains the interconnectivity of the system. It contains the weights that connect the neurons to their neighbors. A typical reservoir creation recipe is the following. The weights of all the connections, so the W in and the W internal, are generated randomly from some probability distribution. Let's say a normal distribution or uniform distribution, typically between -1 and +1. After this generation, after the initialization, the input weights and the reservoir weights are rescaled with given scaling parameters. It can be the input scaling or the internal scaling for the W matrix. This is to adapt the dynamics of the system to the properties of the task that we want to solve. And actually, that's it for these weights, the input weights and the internal weights. We don't tune them, we just leave them random for the rest of the use of the model. The target signal here, the W target, is approximated by optimizing the readout weights only, the W out here. And it is achieved by building a linear combination of the states with the readout weights W. And to approximate this target, we need to train the system. We need to train these weights to solve the task. So the question is now, how can we train our reservoir computer? Well, since one doesn't really train the reservoir itself internally, except, again, tuning these few internal scaling parameters just to adapt the dynamics, you may see the reservoir not as a neural network, but rather as a transformation of the input signal into features that depend on the input history. And on top of that, we build a linear model, which is the output layer. And training a linear model is probably one of the first things taught in any machine learning class. It's the linear regression. And this is actually one of the benefits of reservoir computing. It's very simple to train. So in practice, as you all know, we first define a metric for the error. For instance, the mean squared error here computed between the actual output of the system and the target output, the target time series that you want to reproduce. And we build a mean of that to account for the entire training sequence. And then we find the optimal solution, the optimal output weights of our model, by solving the normal equation of the linear readout. We could also have used the gradient descent, but actually solving the linear equations is much faster. And just a reminder here, big X is the concatenation of all the states for all the times of the iterations of the system. And one last thing, to avoid overfitting, some sort of regularization is generally recommended. In reservoir computing, we typically use the rich regression, which is illustrated here, with the addition of this term here. The intuition behind this additional term is that it increases the error if the weights are big. So in other words, it's penalizing the high weights, and thus it reduces the complexity of the model. Okay, now why did we actually choose reservoir computing as the model to do computation in optics and not some other model that is out there? Well, the key point is that one does not need to tune the reservoir itself, except for the few global parameters. So in simple words, we can take an optical system, basically any optical system with some temporal dynamics, and make it work as a reservoir just by building the readout on top of the system and just training the readout. So now, with this all being said, we can move on to the core of this lecture, where I'll show you several such systems, several optical systems working as reservoirs. They will all have the same readout layer and the same training procedure that I have just shown you, but they differ in how the reservoir is implemented. Of particular importance will be how the nonlinear activation function is implemented. So this, if I get back this element here, this activation function will be different in all the systems. Remember, we've seen it earlier, nonlinear transformations is one of the key ingredients required to do computations, and this is where optics struggle the most. So each system, in each system, I will show you a different way of implementing the nonlinear function, which will be based on the transfer or the response function of the different optical devices. So we'll see two different approaches to optical reservoir computing. We will start with time delay systems, which were first demonstrated experimentally historically, and then we will move on to the large-scale parallel systems. Delay dynamical systems can be found very often in everyday lives. They can also be found in biology, chemistry, physics, engineering, and so on. A simple example of a delay system is the control of the temperature in a shower. Imagine that you take a shower and the water is too cold. So you turn the hot water faucet, but the hot water doesn't come right away. There is a delay induced by the length of the copper tube that brings the water to you. And if you turn the faucet too far, after a certain delay, the water will become burning hot. So you will cut off the hot water again. And if you cut it too strongly, it will become cold again, and so on and so forth. So, under certain conditions, you may oscillate indefinitely between too hot and too cold without ever reaching the right temperature. This is a typical example of a delay dynamical system. Your action on the system at time t at a certain moment depends on the state on the earlier state of the system, t minus tau, where tau is the delay induced. Here, the delay is induced by the pipes of the shower. Consider an example of one of the simplest delay systems here, where we have tau a delay and alpha a certain coefficient that we will keep constant. This system can have heavily complex dynamics, can exhibit oscillations and even chaos depending on the values of the parameter tau, depending on the delay. Here we have three examples. The first one where tau is equal to 7, and here the delay actually stabilizes the system. We start with the perturbation, and the perturbation is relaxed. And here we have tau equal to 8 and 10, and at 10 we can see that here the delay, on the contrary, destabilizes the system and amplifies the perturbations. Furthermore, such systems are very high-dimensional systems because their state space at time t depends on the past history between t and t minus tau. So these systems are rather easy to implement and study experimentally because all they require is one nonlinear node and a delay line through which acts the feedback. In the example of the shower, the nonlinear node is the person that turns the faucets, and the delay is the pipes of the shower. So delay dynamical systems are therefore very good candidates for reservoir computing because they are simple to implement. The fact that a single nonlinear node is required is actually crucial in optics because this means that for a small network of, let's say, 50 neurons, we don't need 50 optical devices to act as nonlinear transfer functions or nonlinear activation functions of the nodes. We can just use one optical device and put the neurons in a queue, like in a delay here in the shower, so that each neuron moves along the queue before it gets activated in its turn. So, how can we transform in practice a delay dynamical system into a reservoir? The idea is actually simple, is to divide the delay loop here. Let's name the delay of duration t, big T. We can divide it into n intervals of durations theta, where theta is just t divided by n, the number of nodes. And we consider each such interval as a virtual node. Virtual here is key because there are no physical things that act as nodes. The nodes here are virtual, they're just segments in the delay. In this way, we create a large number of nodes in the delay. Typically in optical implementation, this large number varies from 50 to a few hundreds, but up to 600s. And when we drive the delay dynamical system here with an input signal u of t, our time series, we apply a sample and hold procedure so that the input is held constant during the delay t. However, this procedure is not sufficient yet because all the neurons, all the n segments that we have defined are identical. They all have the same input and the same behavior, so it's not very interesting. To solve this issue, we will apply a masking procedure. We will multiply the input here that is held constant during the time big T by a masking signal, which will be periodic of period big T. So that this way, each neuron will get a value of the mask. It's like applying the input weights, but here it's in a temporal way. And each neuron will get the same input signal, but multiplied by a different value of the mask. So each neuron will exhibit different dynamics. But it still isn't sufficient to get a recurrent neural network because here we have all the nodes that are independent. So it's not really a network, it's just a bunch of nonlinear elements that form a group. But we want a network that is connected. And for this, we can have two solutions. Two solutions have been proposed. The first one is to slightly desynchronize the time during which the input is held constant and the round-trip time here, big T. So for instance, if we have 50 nodes in the system, we apply an input mask of 50 values, so periodic by 50, but we divide the loop here in 51 segment, or 52, or 53, depending on the length of the desynchronization. In this way, for instance, the fifth masked element, when it gets back through the loop to the nonlinear element, it will be combined with the fourth previous node, and therefore will create a loop connection between the nodes. So the interconnection, this scheme of interconnection will give us the following loop architecture. So we have each neuron will be connected to only one of its neighbors. Mathematically, it corresponds to the W, the big W matrix of this form, where we have all the elements are zero, except one line of non-zero elements here of the diagonal, which symbolizes the fact that each neuron is connected to its closest neighbor. The second idea to introduce interconnection in the system is to use the temporal dynamics of the nonlinear element. And we can do that by injecting the inputs faster than the response time of the nonlinear element to keep it constantly in the transient state. So here we have two examples. In the first case, we inject the elements slowly, as you can see here in blue, and the optical element, the nonlinear element, has time to relax between each injection. So in this way, the neurons are not connected because they are completely independent. If, however, we reduce the temporal distance between the nodes, like this here on the image below, we don't leave the time for the system to relax, and we induce this connectivity because the state of the next neurons depend on the previous states of the system. And this way, by playing with this temporal distance between the nodes, we can connect more or less neighbor neurons together in a pattern that looks like this, depending on the delay that we apply. And now we're almost ready to see some actual photonic implementations of reservoir computing. We just need to review one of the key components, which is a Maxender intensity modulator. It looks like the device looks like this. It has optical fiber going in, optical fiber going out, and a radio frequency port here on the side. One applies a voltage here to the radio frequency port, and this voltage is translated to an intensity attenuation at the output port in optical domain. And this modulation can be done very quickly, up to tens of gigahertz. Inside the optical modulator, typically made of a particular medium, which is lithium niobate, one finds an optical splitter like this, where the light goes either right or left. And then we apply electrodes either to the both arms or just one of the arms. And the electrodes allow to induce a phase difference between the two arms, so that when the arms get recombined here, the phase difference results in a constructive or destructive interference, which acts on the amplitude here at the output of the Maxender. The key notion for reservoir computing in this case is that the transfer function from voltage applied to the RF port to optical amplitude is not linear, it's sinusoidal in the case of Maxender modulator, and it is illustrated on this graph. It's actually linear or slightly non-linear when the modulation signal is weak, and it becomes quadratic for high modulational voltages. So the Maxender is an optical device. This optical modulator is an optical device with a nonlinear transfer function that can be used as the activation function for the virtual nodes in a time delay system. And this is the scheme of such a system. It's actually one of the first systems that were reported in time delay reservoir computing. We will discuss the scheme first, and then I will show the picture of the actual setup. Here we have optical fibers in orange and electric cables are in black. It's composed of the nonlinear node, which is the Maxender modulator here with input fiber, output fiber, and the RF port here. We have a delay line here, which is just a spool of optical fiber of 1.5 kilometers of optical fiber, which induces an 8 microseconds delay. It is followed by an optical attenuator, which allow us to regulate the dynamics of the system and to tune the feedback of the delay line. Then we have a photonic detector, which converts the optical information into electronic information. And we also have an amplifier, simply because the output of the detector, the voltage that we get, is not enough to drive the RF port of the Maxender. So we need to amplify it a little bit. We also have a light source here, an incoherent LED that works at the C-band in telecommunication at 1550 nanometers, the standard wavelength. And last but not least, we have some electronics that generate the signal and capture the reservoir states. This is done on an FPGA, which is illustrated here, because a computer cannot work in real time with this photonic loop. So we have here at the readout a 90-10 splitter. This means that 90% of the signal remains in the loop. We extract 10% to a photodetector that converts the information into an electrical signal and sends it to the FPGA. This is how we capture the states of the reservoir, the X of t. And the introduction of the perturbation signal, the input U of t, is masked on the FPGA and sent through this electrical cable and applied to the RF port of the Maxender. And here is the picture of the setup on the optical table. We have the light source here. Here you may recognize the Maxender modulator, and the big thing here on the right is the spool of fiber. So actually 1.5 kilometers of shielded optical fiber takes some space, and you can clearly see it here. And the rest is just electronics. We have the amplifier here and the photodetectors here. In this system, the reservoir itself is analog, but the output reservoir was computed offline, first on the FPGA and then on the computer. The computer is not shown on the picture, you can only see the screen here. The system can implement networks from 50 to 600 nodes. This is how much we can fit into a delay of 8 microseconds. And we applied this system to a telecommunication task, to the equalization of a wireless communication channel, and also to a simple task of recognition of isolated spoken digit with, again, typically 50 nodes. While the system contains an optical nonlinear node, so the Maxender here, there are still some electronic components in the reservoir. So remember, we still have this detector and the amplifier, which are electronic, and they are in the delay loop, so they are in the reservoir. So the natural step further would be to come up with a system that would have a fully optical reservoir. And here's the scheme of this setup. Some of the components are already familiar to you. We have the LED here as our source, the Maxender the Maxender modulator, but pay attention. Here it's not inside the loop, it's outside, so it's no longer the nonlinear element. It's only used to modulate the input signal. We also have two optical attenuators, one inside the loop and one outside to tune the strength of the input signal. We have the same splitter here for the readout. We have the same delay line of 8 microseconds. And the big difference here is this nonlinear element, which is semiconductor optical amplifier, or SOA. This SOA operates near saturation, so it's nonlinear. And the cavity itself operates below the Leiden threshold, so we don't have the problems with instability. And the key observation here is that the cavity here is fully orange, so it's fully optical. Even the injection actually of the signal is optical as well. Now, this system operated at the same time scale. We have the same delay line here of 8 microseconds. So basically, time-wise, it has the same characteristics of the same optoelectronic setup. Now, let's say that we want to go faster. What should we do? Well, to do that, we need to shorten this delay line to get faster components and get new optical components with fast dynamics. And a good example of an optical device with very fast dynamics is a laser, or more exactly, a semiconductor laser. Here, again, this is another setup of Reservoir, the previous ones. But here now at the injection, we have a laser because we need coherent light in the loop. And the nonlinear element is a laser as well. This laser is driven by a circulator. It's an optical device that allows the light to pass in this direction from the loop into the laser, and in this direction from the laser to the loop like this. So that, and not in any other direction. So we avoid unnecessary reflections back to the laser to destabilize its dynamics. And since the laser dynamics is much faster on the nanosecond scale, actually, we can significantly reduce the delay line, the delay loop here, and pack the same amount of nodes in the system. And to the best of my knowledge, a system based on this principle using a laser holds the record on one of the benchmark tasks in optical reservoir computing, which is the recognition of spoken digit. It was published by a team at Besançon, France. They built a system with a delay line of 63 nanoseconds, so very short, much shorter than the 8 microseconds that we used to have in the optoelectronic device. And this allows them to classify 1 million words per second. So This is how the experiments on photonic reservoir computing started with the time delay systems. Nowadays, however, the focus of the community is constantly shifting away from the time delay systems. There are two major drawbacks, are that they are bulky, tabletop experiments, and their serial architectures. So on-chip integration is the solution to the bulkiness problem, and now is the time where things start to become very interesting. Why? Because the technology of photonic circuitry manufacturing is just about to reach the maturity necessary to the fabrication of integrated reservoir computers. Our colleagues at the University of Ghent in Belgium are actively working in this field in partnership with IMEC, who is in charge of printing the photonic chips. And they have published a few experiments on photonic reservoir computing integrated on chip. Be careful, the IMEC company changed their logo recently, and some employees like to joke that with that logo they also changed their name from IMEC to ONIC, but it is not. It's still IMEC, not ONIC. And for the second drawback of the time delay systems, is that if we want more computational power, we need to increase the size of the reservoir, right? 50 nodes is not that much, and even 600 is not that much for a complex task. But if we want to increase the size of the network, we need to increase the delay line to fit these networks, to feed these nodes into the queue. But to do that, we will have to reduce the speed of the system. So the need for bigger reservoirs working in parallel motivated a new avenue of research in photonic reservoir computing, which is now called the parallel large-scale reservoir computing, which we will discuss in the next section. The parallel systems do not rely on complex temporal dynamics of optical systems. Instead, they exploit the spatial characteristics of light. So far we have considered only fiber optical systems where the light propagates in fiber. It's just an electronic, it's like an electronic wire. So it doesn't really have a cross section, or at least it's negligible in our applications. But in free space, the light propagates as a beam, and this beam has a width, and we should exploit that. This cross-section area of the beam can be used to encode information or emulate neurons on a network. And if we do that, all the neurons will be treated in parallel. So in this section, we will discuss systems where all the neurons function in parallel, and each one of them will have its own nonlinear activation function. We will also use a modulation device because we will encode the information in the amplitude. But now we need one that acts on the entire cross-section on the beam, and that can act locally in different points of the beam, and that's called a spatial light modulator, or SLM in short. It looks like a device like this with a small screen, and then can modulate different properties of light, such as phase, intensity, or polarization, in different places of the beam. They are very similar to a liquid crystal screen. They are composed of the layer of liquid crystals, but they don't have a polarizer on the top. So the electro-optical properties of these liquid crystals enable to locally change the phase of the propagating readout light. If we apply an electric current, it induces a rotation in the liquid crystals, which change the refractive index of the medium, and therefore it changes the polarization of the light. Such a simple device allows to modulate the phase, the amplitude, and the polarization depending on the design of the SLM and also the surrounding optics, so what we put in front or after the SLM. So now that we know that, we can take a look at one of the first, and it was the second to be precise, implementations of parallel reservoir computing in free space. So here the setup consists of an optical arm on the left and the digital arm on the right. We'll start with the optics. We have here a light source. It's again an LED, which is green. So now we're in the visible spectrum at 532 nanometers. It's in free space, so we need to expand and collimate the beam to the right size. And the right size is to cover the surface of the SLM, which is approximately 1 square centimeter. So we have lenses here, and we have a lens here to actually focalize the image on the camera at the end. And we also have two polarizers, one here and one here, with a specific orientation of 45 degrees with respect to the vertical axis, so that to convert the phase modulation of the SLM into intensity modulation. So basically, we are in this scheme here, where we have the SLM sandwiched between two polarizers, so that the SLM itself applies the phase modulation, and the polarizers here in front and afterwards allow to convert the phase modulation into intensity modulation, which can then be captured by the camera, because the camera doesn't see the phase modulation. In this scheme, the neurons are the pixels of the SLM, so the points of the SLM, and their nonlinear activation function is this nonlinear conversion of the phase modulation on the SLM to the amplitude modulation on the camera. And you can see here two examples of the reservoir states captured by the camera. They are 32 by 32, which gives us 1024 nodes, which is significantly bigger than the 50 or even 600 reservoir size that we used to have with time delay systems. And with this setup, with the resolution of the SLM that we had, we can actually push this up to 16,000 nodes, which is a significant difference in terms of computational power. So far we have neglected the electronical arm here on the right, composed of the computer. So let's move on to the next slide and look inside the computer to see what's going on there. So this is the scheme of the same experiment, but now the optics is presented a little bit differently. And what is important is that we see what happens inside the computer. The input signal U of n is generated inside the computer and also masked. So Bij here is the input mask. This signal is applied to the surface of the SLM differently for each neuron because of the mask. The mask here is not a temporal signal anymore. Now it's rather a spatial signal that distributes one input value onto the SLM, different values to the different nodes. So the value appearing on the SLM modulate the phase of the illumination beam coming from the LED. This phase modulation is converted into amplitude modulation through the polarizer. This amplitude modulation is captured by the camera. The camera takes a picture of the SLM and sends this picture to the computer. So this is the recording of the reservoir states. And these states are used both to compute the output using the weights and also used to compute the update of the system. So to compute the recurrency, they are multiplied by the interconnection matrix W, and this term is added to the inputs in the next iteration. So to summarize, most of the reservoir computing in this scheme happens on a computer, and the SLM system, the SLM setup, the optical setup, performs the nonlinear activation function of the neurons. The significantly bigger reservoir size in this setup allowed us to tackle more complicated tasks. As a first application, we tested the system on the handwritten digit recognition task with the MNIST database here, but we quickly realized that using a recurrent neural network on a static image recognition task doesn't make much sense. There is no temporal dependence between the images. In fact, our system basically worked as a feed-forward neural network without the recurrency. So we quickly switched to video processing and tackled the recognition of human action in videos. For this, we used the KTH database, and the task was to recognize 6 different actions, namely boxing, hand clapping, hand waving, jogging, running, and walking. These actions were performed outside or inside by 25 subjects. They are filmed in grayscale without depth information, so basically RGB only. We used a reservoir computer of maximum size of 16,000 nodes, and we obtained an accuracy above 91% on this database. And you can see that our results are actually comparable to state-of-the-art results obtained with deep learning, but on digital computers, whereas we report what we have obtained on a photonic setup. The next logical step is to add more optics, right? So far we don't have much going on in terms of optics in our system. So how about we move on to a more optical setup? And this was done by the team led by Daniel Brunner in Besançon, France, again. He was the first to design a setup with a fully optical reservoir in free space optics. So in this experiment, we have the light source here, and the light path, follow me on this one. So it comes here from the top. Here we have in the middle a polarizing beam splitter, which uses the polarization of the light to direct it in a particular direction. So the light comes from the top, goes on the left, illuminates the SLM. Then it comes back with a different polarization, so it passes through the polarizing beam splitter. It reflects back on the mirror. And then when it comes back, part of it goes back to the SLM and a fraction of it gets deflected to the camera here. So basically, once again, from the top, on the left, right, and either left or the button for the readout on the camera. So here there are two important differences with the previous setup. So first of all, the recurrency of the reservoir computer, or the cavity between the SLM is the mirror here, is fully optical. So the recurrency of the system is fully optical as well. And the second key difference here is this element that I didn't mention, DOE, and it's a fancy name for just a piece of glass that is unpolished. So you can't really see through it. And what it does, when light passes through it, it deviates it slightly on the sides. So remember, in this setup, the neurons are the dots on the SLM. So what happens when we deviate the light from one path to another? Well, we send information from one neuron to another. So we create interconnections. So in this setup, the interconnections are also done optically, thanks to the DOE. They are not, sorry, they are not tunable. You cannot change the particular weights of the DOE, but that's the beauty of reservoir computing. You don't need to. All you need to train are the output weights, not the internal weights. And to go even further, one could replace the SLM by another optical device, such as the laser, again, or in this case, an array of lasers. Distributed spatially, which have a richer and faster dynamics to create reservoirs with more computational power. You may have noticed a similar strategy between here parallel devices and time-delayed devices. First, we build a simple system that is easy to use with simple components. And once we are familiar with the system, we add lasers that are much more complex, and we try to do our best with lasers. Well, that's actually the idea. That's the approach in optical systems. And this is also an experiment on which the team of Daniel Brunner in Besançon is currently working. So they already published a paper on this setup, where they have a fully optical system but with an SLM. And now they're working on a project where they're replacing the SLM with an array of lasers that would be faster and would have a richer dynamics and thus more computational power to do more complex tasks. Okay, we're about to reach the end. So before concluding my presentation, I would like to thank my collaborators. So first of all, Serge Massard from the University of Brussels, with whom we worked for several years on time delay reservoir computing. Then Damien Rontani and Nicolas Marsal who are my colleagues at Centrale Supélec in Metz, and also Daniel Brunner, who is a researcher at Afento ST in Besançon. And with those three, we developed together the free space system, the large-scale setup based on the SLM, that we applied to the recognition of human actions in videos. And since 45 minutes or so is clearly not enough to give you a full overview of the photonic reservoir computing field, If you're interested in learning more, feel free to check out the book that we published a year or so ago on this subject that has many chapters devoted to time delay system, large scale systems, and more advanced setup that I didn't have the time to mention in this presentation. So, in conclusion, we've seen that the idea of optical computing has been investigated for a long time now, but so far optics is waning. But we may want to reconsider this, and we can no longer argue that since it didn't work before, let's not do it. It doesn't work that way anymore. Not only because photonics are getting better, we have new sources, more efficient, we have new waveguide geometries, we have new optical materials that interact more efficiently, we have new integration techniques to build photonic chips. And also not because electronics are about to hit the wall of physics in terms of miniaturization and heat dissipation. No, I think the main reason for reconsidering optics is because our need for computation are actually changing. We need less of accurate processing of numbers or calculations as we had before, but rather more of slightly inaccurate processing of analog sensory signals, such as imaging or sensors from devices. And this is the domain of neural networks. In this seminar, I've shown you some of the ways to do that. So to implement recurrent neural networks with optics using reservoir computing. We've seen systems capable of going very fast. They're time delay systems, or large-scale system with enough computational power to tackle complex tasks such as video processing. So, my final thoughts. Does this all mean that we're about to experience another switch from electronics to photonics in the computing world anytime soon? No, I don't really think so, at least not in the nearest future, because electronics remains a very powerful tool and it is very well implanted in our everyday life. However, I strongly believe that the next generation of high-performance computing machines using large-scale neural networks will be actually opto-electronic, if not fully optical, actually. Of course, after some intense research and development. And with all that, thank you very much for your attention.
Yeah, thank you, brother Piotr, for this interesting talk. And we also have a question from the audience. So it's Alexander Seidel. He also wants to thank you for your nice presentation and wants to ask a question from a non-physicist. How fragile are such optical setups and what are potential strategies to make them work outside the lab?
Yeah, it's a very good question because the two approaches that we have seen actually differ significantly in terms of the stability and all the perturbation that we need to account for when we design them. And it also depends on what type of light you use, right? So if we use incoherent light and time delay systems in optical fiber, it's actually very easy. And this is probably one of the reasons why we start these systems, because the cavities that we design don't need to be stabilized. And we just literally plug the fibers together and it works. If, however, we want to make things faster or more efficient, or we switch to free space or coherent light, there we need to stabilize our light path because coherent light interacts. And if we have the delay loop that comes back with the phase difference that destroys all the signal, it's a problem. So yes, coherent light systems need to be stabilized. You need to stabilize the cavity with a piezoelectric or some PID or some stuff like that. And in free space optics, it's the same. The system is not as fast to be unstable in terms of vibrations and stuff like that. But if we use coherent light, then again, we need to stabilize the length of the cavity so that it remains the same on the time scale of the evolution of the network, so that what the network sees is the evolution of the network and not the evolution of the cavity of the coherent light. Hope this answers your question.
Yeah, thank you so much for this answer. Where do you see the application of your methods? It's in which sector do you think your methods are applied? Is it more or less the medical sector or any sector around?
Actually the question of actual applications of photonic reservoir computing is also an open question which is researched intensely. And the general opinion of the community is that since we're dealing with optics, it would be best and advantageous for the system to use to focus on applications where information is already in the optical domain. Because if you remember, the conversion between optics and electronics is costly. It constitutes an important bottleneck in modern telecommunications. So I would see the use of photonic neural networks either in telecommunications, where, for instance, you need to equalize the channel, remove the errors, or where you would need to route the information. So you choose, you detect the header, you read the address, and you send the packet to the right optical fiber optically without converting it to digital information to electronics. And another applications is obviously medical imaging or imaging in general, where we already have the imaging information coming in optical domain, and where with optical setups we can add several layers of processing or pre-processing, like the convolution, filtering, etc., and where we could imagine adding on top of that a neural network at the end to perform classification, recognition, segmentation, all type of tasks that are usually solved in imaging in general.
Yeah, thank you, Piotr, for this answer. So then we are at the end of our seminar today. So thank you very much to our speaker for this cool talk. And for the audience, thank you very much for listening. The seminar is recorded and will be available afterwards on our YouTube channel. And yeah, we are at the end now. Thank you very much for being there. Thank you, brother, for being our speaker today. And stay healthy, everyone. See you in 2 weeks. Goodbye.
Yeah, thank you for coming. Goodbye.